And so I'm going to talk about how we can take Java programs and symbolically model them as code models. And that's part of the code reflection feature. Then Adam's going to talk about how he takes these Java code models and he extracts machine learning models out from them and executes them in interesting and funny ways. And so that's what we're going to talk about. I would say that the second part feels about Duke reflecting on Duke, reflecting on Duke. There's this sort of cycle of transformations here. And I feel I give a shout out for John Rose's talk on Wednesday about static and dynamic, because what we're doing here is a bit of static analysis, a bit of dynamic analysis, like breathing in, dynamic, exhale, static, inhale, exhale, like this, around sort of a rhythm. And this sort of brought me to the point that the JVM of the platform is static and dynamic, and you shouldn't pick one or the other, because the real power is both of them. And if you choose to go one way or the other way, you limit the power of the platform. And I think when we're looking at code reflection, we're leaning into that on steroids in some respects. But then John will tell you how the platform is leaning in steroids in other ways as well. So all fun stuff. Just a quick status before I get into the details. So we had talks in the previous summits, and I'm not going to go over the same information there. So I'd urge you, if you're not familiar with this feature, to go back and look at the slides and the talks there. So what we've done in the interim is we're really trying to sort of get ready for incubation. I'm not saying which release we're going for yet, but we're really trying to get ready for that. And we put 99% of the code in its own incubating module, which is a really good sign that we're sort of preparing. And I think this will launch us out into other people being able to experiment with this feature. We've been experimenting it with ourselves, but what we need to do is get more feedback. And so this allows us to sort of present this feature in the platform, but make mistakes and fix them before they're permanent. And that's what we want to know about. We've done a lot of work with Onyx and machine learning that Adam will talk to you about. And there's progress on the Heterogeneous Accelerator Toolkit, which is a programming model and platform for leveraging GPUs that leverages Panama and code reflection. And we just have 2 new hires in there too. So we expect to see, no pun intended, more acceleration on the HAT stuff going forward. All right, here are some draft JET goals that when we do have a JET out, that I expect will go in there. And Alex actually helped write these a couple of years ago, and I still think are relevant. So the first 2 goals is what Adam is going to show, is that we're able to interoperate with foreign programming models, a machine learning programming model, using normal Java language constructs. You won't see text blocks. You won't see a sort of horrible DSL building up a tree. You'll see natural looking Java code. And that's the aim of code reflection here. But to achieve that, we need to be able to represent code symbolically. And that's the last goal here. So we need to be able to sort of reflect on the code and represent it in a symbolic format in memory that's suitable to enable the first 2 goals. So I'm going to describe, before I get into the how we model Java programs, which is really going to be, here's an example, here's how we do it, and keep repeating that. I'm not going to describe some formal description because it doesn't exist. And so I'm just going to describe examples, and hopefully that will build an intuitive model of what is going on and how we model programs. But before I do that, I've got to describe the sort of meta model of what a code model is in memory. It's just a tree, but it's a tree of 3 kinds of elements or nodes. It's an operation, body, and block. And the root of the tree would be an operation. And underneath it as childs will be a sequence of 0 or more bodies. And underneath that would be a sequence of 1 or more blocks. Those blocks are actually sorted. I'll get to how we actually sort those later on. And underneath that, the block can have a sequence of 1 or more operations. And so you can see that there's a tree and it nests. Now, some of this may be familiar with C2 engineers a little bit with the blocks, basic blocks, but you notice it nests. And that gives us a power of modeling structured code in Java. There's also 2 interesting nodes in here. One is referred to as the entry block. That's the start of the sequence in the body, and one is called, and the operations, one is called the terminating op, which is the end of the sequence of operations. We can provide a bit of color on what the tree will contain. So the body yields a value of some type. So I should step back up. Beyond the nodes, we have three types of nodes. We have three types of code model items. One is types, value, block reference. A body will yield a value of some type. And a block can declare 0 or more parameters. And an operation can produce a result, each of which have a type. So one interesting deviation from what people might be familiar with in compiler IRs is that these blocks have parameters. They don't have phi nodes in them. And these parameters represent phi nodes, but we can also use them to model other things in interesting ways, as you'll see. And an operation can use a value that has been declared effectively before it in the rules that we're going to define. So you can see in this example, we declare a block 0 has a parameter of P1. It can be used as an operand of the operation, which produces a result, and that can be used by a subsequent operation as its operands or as a block reference. And the block can refer to another block within the same body, like so. And that's how we get a control flow graph of our program. And this is very familiar to compiler engineers, except that it can nest, and also blocks can have parameters as well. And that's how we can sort blocks in reverse post order, which effectively means the earliest parts of the program come before the later parts of the program. And so we can create this in interconnected basic blocks, and yet we can nest control flow graphs together and go down the tree. So that's the base. If you keep that in your head roughly, that's how we're modeling. And that's actually, this structure is actually really quite powerful. And this structure is really inspired by MLIR, if you're familiar with this, and they're using it to model all sorts of kinds of programs at various levels of representation. So what I'm going to do, hopefully you can read that at the back. I'm just going to go from examples, but I'm not going to show trees like I showed before, because they'll be unreadable. Instead, I'm going to show you a textual representation of that tree instead. And so this is used for testing and debugging. You can actually write it yourself, but it's not, please don't think of this as a language that we're not doing anything like that. It's for testing, debugging, and for explanation purposes. That's our primary focus on this. So I have some source code. I have a static method. It takes 2 ints in. It sums them up with a constant and returns it back. And I'm putting the expressions on separate lines for a reason. So here's the actual code model in textual form on the right. This code model has a top-level operation. It has one body, it has one block, and a sequence of operations you see embedded in. And I'm going to highlight some information as we go. And I may get faster and faster as we go along as you pick it up. We'll see. First of all, there is location information in the model. So we can see I've highlighted here the location information for a return statement here. So as we go through and we supply the model to, say, in Adams and Onyx, we supply the location information, which can be used for debugging purposes and so forth and tooling. So we can see the lines there coming in. We actually have a sort of location on the line and the characters. We can actually put more in and put a span in. We're just dropping that information, but JavaC actually provides more. So we may provide a little interval instead, which will give you richer information. So first of all, we model a method as a func operation. So we see the func at the top and its name as an attribute, a property of the operation, like so. We model the body of the method as a body and an entry block, and you can see the textual representation here fuses the body and the entry block together. So the entry block is the parameters of the operation, is the parameters of the method. I'll get to that in a moment. It deliberately looks like a lambda expression on purpose because it's kind of like a closure over code. The body represents some closure over code, sort of a function that can capture stuff from outside it. And the parameters are modeled as entry block parameters, like so. So it has 2 parameters, int A and int B, and we're actually modeling the parameter values. When you call this method, you pass values to it. Java is passed by value. The values are passed. Because this model, if I didn't say it, the way we do code models, I didn't say it if you've already worked it out, it's all in SSA form. And so we pass values in. And we have values as block parameters, 0% and %1, corresponding to the values of A and B if this method would be called. And we're saying we're yielding a type of int corresponding to a return type of a method. The actual parameter variable declarations are actually modeled in line as core operations that are not, there's no correspondence in Java here, but we model the variables as operations called a var operation that says, given the value that I'm being initialized with and the name of it, here is a value that is actually a variable. And so we model these in line. So we see the %0 coming in modeling A, but the actual variable is modeled in line and its value is %2. And then we can operate on it to load and store from it. So we see a load operation there for %2, which is actually part of the A expression inside there. So when we express A, we model it as a var load on the variable that's modeled by the parameter here. And we see the plus operator here is modeled as you'd expect, an add operation, no surprises there. It takes two values in and produces a value out, two ints in, one int out, like so. And we see the literal one here is modeled as a constant but accepts a 1 coming in, like that. Shouldn't be too surprising. And then the return statement is modeled as a return operation, and this is a terminating operation. And it says, well, I'm returning an int value that corresponds to the type that the body yields here. Okay, so you might be wondering, you see a linear set of operations here. For those who are not familiar with sort of compiler IRs and more ASTIs, you might be wondering where their expression tree is here. Where's my tree? I want to see more trees. Well, you can produce this. So here is a rendering of the expression tree instead of a linear set of operations. And that expression tree is just produced by taking the last operation, the return operation, and just traversing up the data dependencies. And you can produce a tree if you want an expression tree like this. And we wrote a blog last year that talks about this in more detail of how you can produce and render these kinds of trees. If you need that kind of form of processing, you can produce them. The trees are there, they're embedded in, they're sort of hiding in plain sight. Okay, what if we just change this method, another example, and then have a local variable instead break the expression up, a plus b, assign it to c, and then do c equals c plus 1. What we see here is we model this local variable in exactly the same way we model the parameters. So we see another var operation in here, initialized with the value of the a plus b, like so, and then it returns another value, and then we operate on that with a var load, and so forth. And we also see a var store because we're updating var c, there we go. So we see a c equals c plus 1, so we load it in, we get the constant, we add the two together, then we store it back. So we're explicitly modeling the loads and stores here. Now, if I change c equals c plus 1 to c plus equals 1, it's exactly the same in the model. The surface syntax does not change the model here. And likewise, if I do this, it doesn't change the model. So we're sort of simplifying some of the processing here. If you had to deal with this on the sort of more AST side, you'd have to deal with these little sort of shimmers in the surface syntax, and we're trying to normalize that. Okay, what if we change it from a static method to an instance method instead? So now A is a field instead of a parameter. And so instead, we need to model this. So where does this come in? Well, it comes in as the first parameter of the method. Exactly the same before, but except we're passing in the instance of this class in effect. We don't need to model it as a variable because it's kind of final. We can just keep it as a value because it's not going to change. And then we pass it in as the first parameter of this, first block parameter. We can change it this.a instead of a, same in the code model, no different. Or we could actually explicitly express this in the source code. How many people knew you could do that? Yes, all the people who worked on Lambda and stuff like this. I think that was introduced in Java 8, was it? Yes. Yeah, so you can do that too, no change in the code model, which is a good sign of sort of mapping one-to-one here. You also notice now there's a field load expression. So this is our first reflective operation. So the field load says, well, I've got to load the field A from this, but I've also got to describe the reference to the field. So what the reflective operations will see, we have references to the thing it needs to refer to. So we see it's represented as a string here. In the model, it would be an instance of something called a field ref, which says I'm referring to a field. And that field reference can be resolved to a Java lang reflect field. It can be resolved to a var handle and so forth like that. So that's the symbolic information we have there. And that's really quite powerful because we have these reflective operations with these effective references, and then we can sort of really easily write programs that do use normal Java reflection to execute. Okay, so what happens if we go back to static methods and change the parameter type of A to a float instead? We have A plus B plus 1. We don't have to explicitly cast it, like Takir was requesting maybe we should be putting a cast in here. But the model has an explicit conversion inside. What we chose to do was to explicitly model the conversions here. This is a choice we may decide to change later. It might be possible as a higher level representation. We can describe that we can lower into this. But these conversions can pop up in surprising places. So we chose to model it explicitly, so you have to do less work. I think that's the key thing. Whatever we do, the person processing this should have to do less work at a certain level. So we see an explicit conversion when we load A, var load of 3, 5, yes, the result of load, we convert it from an int to a float. Now we see there's two conversions here. So why is there two conversions? It's because we evaluate from left to right. So this is nothing explicit to code models, but if we do the bracket around it, we only see one conversion. So it's just following the rules of what our translation does, which might affect your accuracy or not, depending on what you're doing. Okay, here is something a little different. So I said we model structure. In this example, we got some blocks. We've got one block that contains two blocks, and in each block there's a print statement, printing out A and B. How do we model this in code models? Well, it's a Java block operation, and this block operation contains one body that nests the structure of the code. So you can see it following. The block yields a type of, we're using Java types of void, perhaps it should be a general type of unit, but the block yields nothing. And the terminal operation of the block is just a yield of nothing. We have to put something in the model that says, I'm terminating. But you can see it follows the structure. That's a key pattern that I wanted to ensure with code models, is we follow the structure of the code. And we see an invoke operation here. This is another reflective operation. Like with the field load was a reflective. This is an invocation. This, again, contains a reference to the method to invoke symbolically. And we know we're invoking an instance method on print stream here because there's two operands, %0 and %1, but the description only contains one parameter type. So implicitly, we know we're invoking an instance method and not a static method. The arities are different. Okay, what if we model an if statement instead? You'll start to see the pattern replete here. So we model an if statement as an if operation, and we see that it's got three bodies here. One for the predicate expression, one for the then block, and one for the else block. And so little bits of code are being encapsulated in these closures, you could think. So the first body yields a type of Boolean. And you could imagine the specification saying, well, the Java if operation first passes control to the first body. It goes through its sequence of operations. It yields a Boolean, and if the Boolean is true, I'll pass control to the then body. Otherwise, I pass control to the else body, and so on. You can see it flow like that. That's how we may describe it. Okay, notice as well, we've got a terminal operation at the end. Well, code can't reach there. We have to model it somehow. So we model it as an unreachable operation to signal, hey, if you reach here, you've got a problem. All right, also notice that we're testing the value of I here. It's greater than 10. First of all, we have to load the value of I, the variable. And notice it's the variable, the var operation, is defining a variable of %1 whose type is var, but it's defined in the ancestor of where it's actually used. And so you can use, bodies can use values declared in ancestor bodies. Just like the predicate statement or predicate expression in the if statement can use I. So it's approximately following the same rules. It's not quite the same. What if we change it to a conditional operator instead? Well, it's actually almost the same, except we call it a conditional expression. This is an expression now, so it yields a value. So we still have the same predicate body, but the then and else change to yield the value instead. Like so. And in fact, in code, we may be able to abstract the Java if and the C expression together in some common abstraction, potentially, if you want to unify the processing. We haven't done that yet. So there I've highlighted the body and the expression, and then we return, so it's not unreachable. Okay, so how do you think a for statement is modeled? So how do you think it? Any answers to that? Can you guess? Pretty straightforward. It's modeled as a Java for operation. And it's got 4 bodies because there is 4 little bits of code here. There's one is the initializer. In fact, I'll go through it now. You can see a little better. There's the initializer, there's a condition, the update, and the loop body. The interesting thing here is the init bit of code yields variables. You can actually yield 1 or more. And so we have to express that in the code model. And so the body for the init, it yields a variable. It yields a loop variable. And then we pass the loop variable to the other bodies that can operate on it. Like so. Make sense? Some nodding. So if there's more than one variable, instead we'll model it as a tuple. And we would yield a tuple of variables instead. And notice there's a Java continue operation explicitly, because when the loop finishes, it will continue to the next iteration. So we model it explicitly. If we were going to put a break in there, we check the value and have a break. Well, we would model it as a Java if there, and then you'd see a break in the then body, like so. So the Java break statement, the break statement is modeled as a Java break operation, which is a terminating operation as well. Here's something interesting. Did you know you can label any statement in Java? That was my initial reaction as well. I laughed too. You can. This is useless code, but we still have to model it. But it's actually interesting because of the way I've tried to model this. So we have a block, we can label it, and we can break to it. And we model the label as a label operation that has 1 body inside it, that has 2 operations. First operation is a sort of synthetic operation. We're using the constant operation to express the symbolic value of the label. And then we have the next operation, which is the thing that we're labeling, in this case, the Java block operation. And in there, we have break. And because of the rules of how we refer to values, we can refer to that constant. And we know which label we're referring to because we've defined the rules appropriately in their relationships. So that's how I modeled it. I thought about it for 10 minutes. There may be a better way, there may not be. But you can see the expressiveness of the code model allows us to do this kind of thing. All right, this is what I said, yes. Okay, I'm going to go on to one thing quickly for patterns. We can model patterns as well. So we can model an instance of string S as a match. We model this as a pattern match operation that has 2 bodies. One is the tree of the pattern, and one is the action we perform on it. And so we can specify the variable at the nearest, just before the nearest statement that is a variable for a pattern, and then we assign it in our match like so. I'm not really explaining because I'm running out of time. I just wanted to show you that we can also model complex patterns as trees. You don't have to model explicit code in a body. You can actually model a tree of patterns using a data dependency as well. So you can I can produce the expression tree for the pattern like I just produced the expression tree for the arithmetic operation, like so. And we have a workshop later, so I can go through this a little bit more if people want to see it. There is some tooling implemented by Gary Frost to actually view code models. And I've linked in here, so you can view code models side by side with their dependencies and what they relate to based on the location. You can splice them together, and you can view SSA graphs as well.